So we have a linear combination of some quantities, and we want to adjust the coefficients in this linear combination to be optimal. Optimal in this case means there is a certain target. In our particular case of communications, it can be the plus minus 1 value, and the mean square error from the plus minus 1 value is what has to be minimized. So we have coefficients C1 and Cn, and we have Y. So what we do is, in case of binary transmission, we put it through a comparator. In case of larger number of levels, you have to have a decision that divides it into a larger number of values. Okay. If you have PAM4, for instance, your decision maker will give you 4 different values. In this case, we will assume just 2. I will call this Y hat, and I take the difference E between Y and Y hat. Now I also know that in this case the X1 and Xn can be anything, but in case of the equalizer, this X1 to Xn are delayed input samples. Okay. The delayed input samples are weighted and summed together, and if the equalizer transfer function exactly inverts the channel, that is, it completely removes the intersymbol interference, what you see here should be only plus minus 1 values. Okay. The values should be plus or minus 1 if equalization is perfect. So that is the state to which you want to drive the equalizer. And I illustrated this with a single coefficient, in which case it's more like an automatic gain control. You want to adjust, you have X and you have a coefficient C0, and you want to adjust it so that the samples here are plus minus 1. There are various ways of doing it. I was doing it through this LMS algorithm. This is known as the LMS algorithm because it minimizes the mean square error. And of course the point here is that the X1, X2, the entire sequences are not known in time. You need to be able to update the coefficients as the inputs come, and over time the coefficients should adjust themselves to the right values. Right values meaning again the values that give you the smallest mean square error between the actual Y and the desired values of Y. Okay. What did we do? What was the idea? So in this case, if I want to update C0 at time k is C0 at time k minus 1, you do something to it to update it. What do you do? So we took mu by 2 times the gradient of the mean square error, that is, and the gradient with respect to the coefficient, and that turns out to be this will give you 2e times the gradient of the error with respect to the coefficient. The gradient of the error with respect to the coefficient is the input itself in this particular case. In case of the single input, the gradient with respect to C0 is x. So you take the product of E and x, and you also have a scaling factor mu that will tell you how much you move. It's also important, as we saw from the curve, that if you update the coefficient by a large amount, it can go in the other direction, meaning the error can be large but in the other direction. So it will, at that point it won't converge. It will keep swinging between points of large error. Okay. So the mu has to be small enough. We'll see exactly how it is related to the filter. Mu has to be small enough in order to give you convergence to a minimum. Okay. Convergence of E to a minimum.
What is the E to X? Is it E of n?
Yeah. So in this case, so we can see later what exactly it should be, but yeah, this is sorry, k minus 1, that's right. Okay. So you get the samples of E and X, and you multiply the two to do this. And mu determines the step size, right? What happens if mu is too small? Is there a problem? It will just take a long time to adapt. So that is usually not a problem in the kind of systems that we are discussing, because typically all this broadband communication stuff, it can take some time to come up. Okay. For instance, when you plug the Ethernet cable, it's okay for it to take even a second for everything to come up. But after that, it should track the variations. Those variations are slow. So it's okay for the adaptation to be somewhat slow. Of course, each standard has its own definition of what is slow and what is fast. But you don't expect really rapid changes and expect adaptation. So using a small value of mu is safe because it will always converge, but it will become slower to adapt. So in case of an FIR equalizer, we have I'll show it as though the input itself is in discrete time. So this could be, let's say, the output of a sample and hold in a receiver, and so on. You can have a number of these stages, and you sum them to get the equalizer output, and you do exactly the same thing. You take the 2 and subtract to get E. Okay. So in this case, Y is, so if it's an nth order equalizer, it will look like this. E is Y minus Y hat. What is the gradient of E with respect to the coefficient Ck? If I do this, this is, okay, this is always true. Now I need to find the gradient of E with respect to the coefficient Ck. What is it? X of n minus k. So from this, so the gradient with respect to this coefficient is this, okay, because I am taking the product of this value and this coefficient C1. So the gradient with respect to this C1 is whatever value I see here. So every coefficient can be updated like this. So I kind of change the indexes and probably confuse the symbols, but so I'll use n for time. I think that's best. For every coefficient you will have this. The equation can get kind of confusing because you have too many subscripts and the time variable also. But the idea is the error has to be multiplied with whatever the coefficient is multiplying. Okay. There is a coefficient for some value, some quantity. So in this case, x of n minus k is what is multiplying Ck. So to update Ck, that is the value that you are concerned with. Okay, that should be multiplied with the error, and you need to update the coefficient like this. Okay. And for every coefficient you do this. This kind of LMS adaptation can be done for any kind of system, but it is easiest for FIR or somewhere where you have a linear combination, because the gradient is simply whatever the coefficient is multiplying. Okay. If you have this linear combination form, the gradient with respect to Ck is x of n minus k. Okay. That is what makes this whole thing convenient for FIR filters. It could be a more complicated function. You can do LMS adaptation potentially even in that case, but in this particular case, it's very easy to find the gradient. Okay. Any questions on this? So I do this for every coefficient. That's all. Every coefficient is updated based on the error and whatever each coefficient is multiplying. The error is the error in the received value with respect to the target. Error in the output value Y with respect to the target. So every coefficient is moved so that the error in this is minimized. Okay. Oh yeah, it should be, right?
So the equation, if n is referring to the n set of, what does he refer to?
The error at the instant n. At every instant n, instant meaning every sampling instant, you do this. You update Ck such that you take the current value of Ck and mu, the current value of E at this sampling instant, and current value of whatever this is multiplying, x corresponding to k. So what's the problem here?
The updating of channel coefficients.
Yeah. No. It is it's the same thing. I mean, it can be slower. We will discuss those things. But at every instant, if I look at this equalizer, I have a certain value y and certain value y hat. From that, I calculate E. Okay. And at that instant, I also have, let's say, I am interested in updating this coefficient. So at that instant, I also look at this. So I multiply this with this and use that to update this particular coefficient. Similarly, at the same instant, I look at this and use that to update this particular coefficient. That's what I do. Anything else? Is this sufficiently clear? Yeah, that's what. I mean, for now, you can assume that it should be sufficiently small. Okay.
If it's large, you should be doing more other direction.
Yeah.
Only converts back to the.
Not necessarily. Okay. It's easiest to say it with one or two coefficients. I'll show it for one coefficient. So let's say we have this system, x you multiply by C0. The only variable here is the value of C0 that we need. And finally, I want the samples of this to be only plus minus 1. Basically, this is automatic gain control. So the error E is y minus y hat, and y hat is either plus or minus 1. Okay. So E square is what? C0 x minus y hat square, which is With respect to C0, it's a parabola. Okay, the coefficients depend on x and y hat. It will do something like this. Okay. Now let's say the value of C0 is here, and the value of mu is such that, say, the update depends on the value of x itself, x and e also, but let's say that the update value is mu times e times x. So initially let's say the coefficient was this, okay, and mu times e times x takes it here, and the next time it could take it here. No, that depends on the value of e and x also, but e is larger, right? No? Yeah, negative feedback doesn't necessarily converge, right? You can oscillate in the direction of the gradient, right? You want to make it negative feedback. But see, this is a discrete system, meaning it's a negative feedback system with a delay. Okay? Meaning you measure something in one step and you do something in the next step. So with that, like for instance, if you have this and you have let's say this is an op amp with saturation, okay, and you have a delay, what do you think will happen? Will it be stable or not? This is an ideal op amp. It won't be stable. Why? Because I asked the question. Okay. Huh? 1 plus e to the minus st. How do you? It has poles on j-omega axis. Yeah, that's right. Yeah. So, but it will have right half plane poles for sure, right? So it will be unstable. So actually, let's in fact, this is a somewhat instructive example. So the way you think of this negative feedback is, I mean, the way you normally analyze these negative feedback systems is that you have some equation for the forward amplifier and some equation for the feedback, and the simultaneous solution to the two is the solution to the system. Okay. Now, the forward amplifier has a characteristic like this. In fact, the slope will be even more exaggerated in reality. Okay. And the feedback amplifier in this case has a slope of feedback characteristic has a slope of -1. It can be, if you have a resistive divider, it will have a slope of something less than 1. So if you don't have any delays in the system, I mean, these are supposed to intersect at the origin, but you get the idea. You have no delays, simply there is no evolution in time, right? You simply get these two equations and the point of intersection is the solution. Okay. Now let's say you have some delay, and let's say the initial value of this is not 0. Okay. So the initial value of the output is some value. Let's say it happens to be. So what happens? You look at there is a delay, there is some initial value. After the delay, this comes here. Okay. And the op amp will give you an output corresponding to that particular input. Okay. So if you start from this point, so you look at this is the input to the amplifier, right? And this is the output of the amplifier. So the output of the amplifier has an initial value of this. So that corresponds to an input of this value, which gives you an op amp output here. And that output, after a certain delay, causes the same input. So it will go here, and after a while, so simply it will be oscillating. Okay? The trajectory of the oscillator will be like this. So if you have a delay, this is a negative feedback loop, but if you have a delay like this, it will oscillate. And you must have evaluated while, if you have done this numerical, algorithms for numerical solutions and so on, you know that if the product of these two slopes is more than 1, you will get oscillations, right? Are you familiar with this? You can get, so one way to solve nonlinear solutions is to get it in the form of f of x equal to x. So this is like a negative feedback loop. So essentially you are trying to solve, if you think of this as a circuit, you have a forward amplifier which realizes a f of x, and the feedback is x, and you are trying to make the two equal. Okay, f of x minus x equal to 0. So any nonlinear solution you can try to get it in this form and solve it. And there that's the idea. So to get the solution to a nonlinear equation, here what the equation that you are solving is f of x minus x equal to 0. So there are many, any nonlinear equation potentially can be turned into this form, right? If you want a solution to g of x equal to 0, you make g of x plus x, this as f minus x equal to 0. Then this is known as fixed point iteration, right? Are you not familiar with this? Okay, this is something, I'll not spend too much time on it. But one way to solve it is f of x equal to x. And let's say you start with an initial guess for x and you calculate the value of f of x. Okay, and then you feed it back to the same function. Okay, that's the idea with the fixed point iteration. So for instance, let's say your initial value is x naught. So in the first step you calculate f of x naught and that is your x1. Okay, in the second step you calculate f of x1, x2. Now this could potentially converge, in which case you get the two to be equal to a sufficient degree and then you stop there. That's the numerical solution to this problem. But it's not guaranteed that this will converge. So what happens is, if the slope of f of x, so let's say f is something like this, if the slope is more than 1, it can diverge. Okay, so it doesn't always converge. In general, you can, if you have, the idea behind fixed point iteration is what I illustrated before, that you look at the output, you calculate the input, you look at the output corresponding to that, and you go here, and this can either converge to the intersection of the two. This is a very bad graph, let me redraw it. So this is x, right? This is a slope of 1. And then you have some other curve, f. And here, f of x equal to x, you are trying to solve for this point. And let's say you start off from somewhere here. What do? You calculate the x based on f, and you calculate f based on that, and so on. So this process can diverge or converge depending on the relative slopes. So similarly here, if you have a delay, you can go from this point to this point and then here and then so on. Or it could be oscillating between points of equal error. Okay, that is certainly possible, right? If in this particular case, maybe your step is like coincidentally happens to be such that your error is negative and in of the exactly the same magnitude, then your update value mu times e times x won't change. The magnitude of that won't change. So you will go here and then come back here, and you can oscillate between the two values. It is possible. Or if your step is very large, you can even go off because you can go off to larger and larger errors. No, at this point it's a discrete time system, right? It doesn't influence it at all. Because I only have, the value of t is kind of irrelevant for this. I have a discrete time signal and I make an FIR filter and I update the coefficients of the FIR filter. This one, no, it doesn't influence it. What, you tell me, what's the role of t here? I said that it gives you instability. How will t show up in the result of the circuit? No, but the analysis I showed you was not dependent on the value of t. The frequency of oscillation is the only thing that is determined by t. Okay. So in this particular case, if you have an op-amp with saturation, it will always oscillate. I am assuming that this is a memoryless characteristic. That is, it doesn't have any poles inside it, and it has saturation. Okay. And there is a certain ideal delay t. So what happens is eventually, because the gain of the op-amp is high, that's the assumption, it will always oscillate between 2 points in the saturated region of the op-amp. Now how fast it goes back and forth is determined by t. What will be the period of oscillation? 2t, right? So it will do this. So each one will be t. Okay, the output of the op-amp will be something like this, that's all. The slope is not dependent on t at all, right? See, these, the characteristic I drew was basically V0 versus Vi of the amplifier. Okay, so there is no t here. Which, yeah, but how is that dependent on t? That's like the DC value of the signal, right? So you are talking about this one, right? Yeah, the slope of this is 1. I mean, that relates, that is the gain of the feedback system. That is, the magnitude is 1. So the delay will influence, I don't know what happens when t equal to 0. That is too many, it's probably a complicated singular case. But at that point you can't say, I mean, even the language becomes difficult, right? You can't say the output goes here, then something happens and so on. There's no delay, it will just stay in one state, whichever state it is. And in this particular case, it can only be in this particular state, that's all. If t is 0, nothing is changing with time, that's the bottom line. So, I guess now it is convincing that if the step size is large, it can oscillate, right? T equal to 0? Yeah, that's correct. So, I mean, I am analyzing this thing with input equal to 0, right? This was 0. This line depends on the input. When I have this, the standard op-amp analysis, this Vi here is the differential input of the op-amp, not the input to the circuit, okay? VID and VO. And let's say this is the input Vin. And VID is what? Vin minus V0 times R1 by R1 plus R2. So, if Vin is different from 0, this line will be shifted. Okay. So, let's say I have 1 volt of Vin, then the solution should be here. And in that case, it will correspond to that 1 volt line. Okay. So, this line that was passing through the origin corresponds to Vin equal to 0. Okay. So, the bottom line is when we have a linear combination, that is a number of quantities being summed together to get a linear combination, the output, the mean square error of the output can be minimized by updating the coefficients in a certain way. And in this particular case, the gradient turns out to be in a simple form, relatively simple form. That is, you have the error and you have the input to that coefficient, you multiply the two and that gives you the update for the coefficient. You have to scale it by some value mu so that the update is small enough so that convergence is guaranteed. Okay, that's the bottom line. It's very simple. Now, how do we implement something like this? So, we have this and we have to implement this equation. How do we do that? So, let's say we have some cell which has variable coefficients, okay? That's not a problem. Meaning, just like we made it for the transmitter, we have, for instance, the coefficient can be realized as a transconductor, as a differential pair with variable tail current or something. So, we know how to realize variable values of Ck, okay? But how do we implement this part? What do we need to implement that? So, you need to generate the product, that's the bottom line, right? You need to multiply x with E. How do we do that? What are possible ways of doing this? Basically, we need a new block that we have not used before, that's all. So, we need to be able to multiply the signal with the error. Yeah, so I mean some implementation of an analog multiplier, that's what you are suggesting. Yeah, that's potentially, that is doable. So some implementation that can be based on this difference of squares, or it can be based on exponentials or log. Okay, so that's analog way. Or when I was discussing receive equalizers, I said one way was that we sample the signal, we convert it to digital. In that case, we multiply in the digital domain. So, x of n minus k is the quantity that is multiplying Ck to get the output y. So, you need to generate the product. Mu is fine, it's just a scaling factor. X of n minus k. So, if you already have the signal in digital form, that is fine. So, that is x of n in digital form. If x is in digital form, that means that y is also in digital form. So, basically y minus y hat will be some number and you multiply that by x, okay. So, basically you need a digital multiplier to do this, okay. Or you can think of analog multipliers to implement E of n x of n minus k, okay. Or you can have x itself in analog and just to multiply you can convert E into digital format and try and do that, okay. All those things are possible. But the problem is if everything is in digital format, you can do it somewhat easily. But it looks like if your equalizer itself was analog, let's say you made a sample and hold based equalizer, then all your quantities are analog, right. then just to do the coefficient updating, you need to implement the whole thing in a digital domain. Or you have to make an analog multiplier, which is also not simple to do. So, but again, you don't want to use A to D converters, because if you use A to D converters, perhaps you could make the whole thing in the digital domain. So now, what can you do? What is the resolution required in the A to D? That is, let's say I have an analog equalizer, and I have X, which is analog, and I have E, which is also analog. Now I want to convert it to digital and implement this algorithm digitally. What might be the resolution required? Still, it's not, I mean, this is a very vague question. You can't give a quantitative answer, but it turns out that you can use 1-bit resolution. Okay, that is, you make in calculating this product, you make the resolution of E and X cruder and cruder. Okay, so finally, when you get to just 1 bit, okay, this is just for coefficient updating. That is, you instead of doing mu times E times X, you can do mu times sine of E times sine of X. Okay, you quantize both E and X to 1 bit and do the multiplication. It turns out that also works. So, to simplify the coefficient updating, you can use maybe the sine of E and the value of X, or you can use the sine of X and value of E, or you can use the sine of both. Meaning, this is simply, you can think of converting these values to digital with lower and lower precision until a point where you only detect it to 1-bit precision, where you simply see whether it's positive or negative. Not necessarily. It can take shorter time also, right? Because if you quantize it, let's say the value of E itself was very small and X also was small. So mu times E times X will be some small number. But mu times sine of E times sine of X will always be mu. Meaning it's either plus or minus mu. Okay. The update of the coefficient, the size of the update is more when you do sine. So this is to, you simplify the coefficient updating, you only quantize E of n and X of n minus k to 1 bit. This again, I want to stress that this is not in the computation of the filter output. The filter output is computed in an analog way. You find the linear combination of C0 x of n, C1 x of n minus 1 and so on. You don't quantize X to do that computation. It's only to do the coefficient updating that you do this quantization. Okay. So this is known as sine LMS, that is, you take the sign of the error and the sign of the gradient. So this again I remind you is the gradient of E with respect to Ck. So you take the sign of the error and the sign of the gradient. What is the potential problem with this? And diverge, why? Let's say I make mu smaller. I mean, if I find that it diverges, I make mu smaller. So let's again take the one coefficient example, or the automatic gain control. This is E square with respect to C0. Now the step here is mu times E times X. Now as you get closer and closer to the minimum, the value of E itself is getting smaller and smaller. So the step is also getting smaller. So ultimately, I mean, in the limit that it actually reaches here, it won't move because E itself is 0. Okay? Whereas that's not true when you do sine. You will always have a certain step because you do the quantization. So it will be, you can use a small value of mu so that it converges, but it will be chattering between 2 points on either side of the minimum. Maybe 2 or more points. Yeah, that's possible. There is something known as, in fact it's quite common in adaptation, because initially you want a crude adaptation, you want a fast one, so you use a large value of mu, and as you get closer you use a small value of mu so that adaptation noise is small. This is known as adaptation noise, okay. This kind of thing, the coefficient finally will not settle to a constant value in any case because of noise and other things. So that is the other reason why you have to make the value of mu sufficiently small. First of all, of course, it has to converge, that's a basic thing. But then you can, from one step to the next, in this particular simple case, it looks like it can go to 0 and sit there. But in case of an equalizer, it may not be able to do that. Okay, it may never actually go to E equal to exactly equal to 0 and the coefficients are held steady. Okay, there will always be some value of E. So the error will be oscillating between positive and negative values. So this quantity will keep changing the coefficients in some way. Because the coefficients are changing, the output will also be changing in some way. So there is something known as adaptation noise. That is because of the resulting chatter after the loop is supposedly settled, after the adaptation is supposedly settled. Okay. Yeah, that's possible. So again, this is also done sometimes, that you adapt for some time. So maybe it can be related to the magnitude of V, or maybe it's just like you wait for a certain amount of time. That is, you know that it's going to take this much time to adapt, you leave like maybe 5 times that time and then stop the adaptation engine. In that case, the coefficients will be steady. So the adaptation noise will be 0. What is the risk in this case? What's the problem? No, I mean, let's say it has converged. Yeah, if the channel or the conditions vary, you won't be able to adapt it. That's all. So yeah, all these things are practical things that are done, and in fact this is how you come up with it also. When you are designing, you find that something is annoying you, then you can't just follow you can't be this by the book LMS type of guy, right? So you have to make this kind of ad hoc modifications to the algorithm to make it better. Okay. So yeah, you can you can change the value of mu. That is actually done quite frequently, that because initially you want a fast convergence, you don't want, and maybe like let's say at the end you want a really small value of mu, but if you start off with that, you will take a very long time to build up. You don't want to do that, so you use a large value of mu. Now it is able to converge to somewhere around the right value. Then you reduce the value of mu so that the noise gets, the chatter gets smaller and smaller. Or like he suggested, you do initial calibration or initial adaptation and stop, and you can do it periodically. In many systems it's done. See, there are systems in which interruptions are allowed and there are systems in which interruptions are not allowed. Okay. So when you are having a telephone conversation or something, you can't have interruptions. You can't say that, oh, every 5 seconds I'll take some time to adapt so that you can't hear me or something. That's not allowed. But let's say you are, one of the things in which you need equalization, it's not a communication link, but it is very much similar to what we discussed is a hard disk drive. Hard disk drive stores bits on a magnetic, it's a magnetized disk, and it stores bits on it. And as you pack more and more bits, the area available for each bit is very small. So the magnetic field of one particular bit influences other bits. So you have intersymbol interference exactly like what we have with a low pass channel. Okay. So, but here, for instance, this whole process is transparent to you, right? The reading the data and so on. So maybe you can adapt for some time and then you can read the data for some time and you can adapt for some more time and you can do all of that stuff. Because interruptions are allowed, you can use some time to calibrate your circuits. So can you intuitively say what's happening here with sine LMS? Or you can think about it, I think we are out of time, we can discuss it in the next class. What is the meaning of this? It turns out that this can be, kind of stated in words very easily. If you by looking at the value of y, you want to get it to the right value, you can see what's going on in this. Okay. So you simply look at whether y is greater or lesser and then you change the coefficients in one way or the other.